excited to be here. I'm Jonathan from the Go team at Google, and I'm going to talk to you about fast structured logging. And in case you're wondering, you actually can't see the background on the screen, but if on the actual slides, if you look at the PDF that'll become available, there's like an old captain's log from a ship in the background. So in Go 121, we're going to have this new package called slog that does structured logging. I'll give you a very quick overview of slog, and then I'm going to talk about why we felt we needed to make it fast, and then how we made it fast. First, a bit of slog. So it's a structured logger, so that means there are key value pairs. It outputs key value pairs, which I'll call attributes throughout this talk. And those are great because you can write programs to easily filter or change or aggregate those logs. Unlike the built-in log package, slog also supports levels, and it supports changing output format by installing a handler. I'll have a lot more to say about handlers. But the two built-in handlers give you these outputs, key equal value format and JSON. So here's some slog code. Right here in the middle, we're constructing a new logger using the text handler, writing to standard out. And then we log something at the info level with the message processed item, and then 3 alternating keys and values. And the output is, as I said, key equals value. Now, that's fine, and we expect most people will use that API. But if you want to do it quickly, if you want speed, use this log adders method instead, which takes a few more arguments. And it uses these adder things, which are the key and value together. And I'll explain in detail why that's faster. But you construct them by type. And some people prefer this anyway because you don't get confused which argument is a key and which is a value. And the output's the same. So that's all you actually need to know about slog for this talk. But you can always go to pkg.go.dev. I had up there, in the exp repo, golang.org/x/exp/slog, you can find the experimental version. And you can also, if you go to @master, log/slog at master, you should be able to see the version that's not released in 121 yet, but will be. And 121, I think, is due out around August. So why did we feel we had to make slog fast? Well, here's one answer. Logging is often in the inner loop. Servers do thousands of requests per minute. Each request can generate thousands of log messages. Each log message can take significant time to process. That's not a great answer because why couldn't we just write it in good, clean Go and maybe it'd be fast enough? So the real answer is we have to look at the history of structured logging in Go. So the first one 9 years ago was Logrus. And that's still very popular, even though it's no longer maintained. Still 99,000 importers, but it's relatively slow. In 2017, the engineers at Uber noticed that logging was consuming a significant amount of their server's CPU. So they wrote a faster logger called Zap. And Zap is also quite popular, and much, much faster than Logrus. And that spurred the community to go even faster, so there's a whole bunch of loggers that are faster than Zap. Zero log probably being the most popular of those, although it's not nearly as popular as Zap. And so based on this, we decided to aim for Zap-level performance because we felt we'd captured the majority of people's use cases, since Zap was still quite popular and Logrus too. We did look at trying to get to the level of zero log, but when we look carefully at the zero log API, which is lovely, by the way, we couldn't quite see how to do it and keep it safe. Zero log actually has this subtle use after free bug, and we couldn't figure out how to get rid of that. Now you may wonder, how can you have a use after free bug in a language that has garbage collection, automatic memory management? And I will answer that question later. So that's why we made it fast. How did we make it fast? Well, we followed this 5-step program. So there's five steps here. And the first is probably the most important. It's know what you want to make fast. You can't make everything fast. You have to pick the common cases. And how do you know what the common cases are? You have to look at what's out there that does similar stuff and analyze it. And people often say, why don't you add all this stuff to the standard library now instead of waiting 10 years? Why did you wait 10 years? Because now we can look at what's out there and design the right thing for the community. And part of that was this discussion. I'm only going to mention it briefly now, but yesterday at the panel I talked at length about our process for coming up with the slog API. That was really valuable for features and API. But when it came to actually performance, like actual numbers, the best thing we could do was to look at what was out there. So I searched through a lot of the popular log package importers, and I aggregated some information. So I'm going to show you two graphs that relate to Zap. So here you see the cumulative distribution of the number of attributes, key value pairs, in calls to Zap. So on the slide you see an example of a Zap call to the info method that takes 3 attributes. So that's 3. And I just did a cumulative distribution here. And you can see something pretty striking, that once you get to 5, you've pretty much covered 95%. And adding more doesn't change that very much. Of course, there's a long tail. But 5 is sort of this magic number where you've captured almost all the calls. I was also curious about these types, like we saw zap.string, zap.int. Zap has like 32 of those, and generally in the standard library we don't have 32 of anything. So I wanted to see if I could get that number down. And indeed we see a similar picture where once you get to about 8, you're at 95% of everything. So slog only has almost the identical constructors, but only about 8 of them. So now that we've looked at the data, we can write benchmarks that capture our expectations. So here's a typical slog benchmark. The first thing to note is I'm using this run parallel call to the benchmark code in Go. And that's because you typically see logging in a highly concurrent environment. Servers typically start up a Go routine per request. They process many requests simultaneously. So we wanted to understand the performance when all those concurrent things are happening. We focused on calls with 5 attributes. We found that was our sweet spot, right? And we used common attributes based on that second graph I just showed you. We also tested for more arguments just to make sure there was no performance cliff. We looked at up to 40 arguments just to make sure we weren't doing something horrible there. Here's a general tip. You should always write a call in a benchmark as it would appear in user code. It's very tempting, if you're doing 5 arguments, 10 arguments, 20 arguments, 40 arguments, to make slices of those and to make a loop and do all the stuff you usually do when you write code. But that would be a mistake here, because if you made a slice of these 5 things and passed it in with ... the compiler would generate different code and you get different numbers. Wrong numbers, since most people just write it inline like this. So write your benchmark calls the way users actually would use your API. Last but not least, here at the bottom of the slide, where none of you can see it, there's the link to this wonderful program called BenchStat that other people on the Go team have written. If you're doing any sort of performance thing where you run some benchmarks, then you make changes, then you run benchmarks again, this will take those 2 sets of benchmarks and compare them, tell you the percent speed up or slow down, and also tell you whether that's statistically significant and whether you have to gather more samples. It's a really great tool that I recommend to anyone who's doing this sort of performance work. OK, so I'm going to switch now to the topic of API. So this is the architecture of slog. There's the user-facing logger thing. And the API for that, I'm going to talk very little about, actually. What I want to focus on in this section is the back end, the handler, which is the thing that the logger calls. The logger takes your info call or whatever, bundles everything up into a record, and gives it to the handler, and the handler can do whatever it wants. Handler is an interface. So you can write your own, you can use the built-in ones, and it can do whatever it wants. So you might expect from this that handler would have one method called handle that takes a record. And indeed it does. But it also has a few other methods that are there solely for optimization. And I'll just talk about these 2 on the screen. So many, if not most, log lines never actually get executed. They never actually produce any output because they're there for debugging. And you only turn them on when you really need to. So those should take as little time as possible. And that's what the enabled method is about. The first thing that slog does, that the logger does, is called the handler.enabled method down here. And if that returns false, we're out. We don't do anything else. So minimal processing. So that's an important and somewhat obvious optimization. The next one with adders is a little more interesting. So what we notice by looking at all this code is that people build their log lines in 2 phases. Almost all the loggers have this feature, and this is the way it looks in slog. You can take a logger, and you can say .with, and then you can give a bunch of attributes, and those become part of the logger and will be in every log call that you make with that logger. So here we're taking L1, adding a request attribute to get L2, and then doing some logging with L2, maybe twice or maybe 1,000 times. And each call will include all the things that you write in this info line, like A or B, but it will also include request. Now, converting that R argument, the request, let's say it's an HTTP request, a pretty big thing. Converting that to a sequence of bytes might be rather expensive. So if we could pre-format, if we could do that conversion once when with is called instead of every time when you actually log, then we could get a big performance speed up. And that's an observation Zap made. And so I basically stole this and many other things from slog from Zap. Thank you, Zap. So what we do is the logger with method immediately calls the handler with adders method, so the handler can optimize these attributes by pre-formatting them. It doesn't have to. It could just save them and then use them later as part of the regular logging process if it doesn't want to do that work, but at least has the opportunity to do that. Now, these last 2 points, I have to insert a warning here. I'm going to talk about low-level optimizations. And everything I'm going to tell you is wrong for almost all the time you're writing code. You should only do these things when you need it. I will repeat that several times. In case there are new Go programmers in the audience, I'm going to show you these are advanced performance techniques, not normal coding. So the first is about avoiding indirect calls, by which I mean a call through an interface or through a pointer. Now, that is a little bit slower because there's that level of indirection, but more importantly, it squashes optimizations that the compiler can perform because the compiler can't see exactly what code you are calling at the call site. So the compiler can't inline that code, which saves you the function call, but more interestingly, enables further optimizations because now all this code is in one place and the compiler can think about it. And it also disables escape analysis, which I'm going to talk in detail about in a minute, but which has to do with memory allocation. So for these reasons, logger is a concrete type. It's a pointer to a struct, and not an interface. Now that's just a very vague idea. Well, I'm going to get precise about exactly how that saves allocations in a second. So the rest of the talk is about avoiding memory allocation. We'll go over several scenarios, and I'll show you how we can avoid memory allocation in each one. By memory allocation, I mean heap allocation. The other kind, stack allocation, is very fast. To allocate something on a stack, you increment a register. To free it, you decrement a register. Heap allocation will never be that fast, even though Go's heap allocation has improved over time. Could never be that fast. So heap allocation is always slow relative to stack allocation. And furthermore, it creates garbage, and the garbage collector has to spend time collecting that garbage. By the way, I want to mention a talk yesterday that was about memory usage. Here I'm talking about memory usage indirectly, allocation as it affects time, not as it affects space. So who decides whether something goes on the stack or the heap? The compiler decides that by doing this static analysis called escape analysis. It looks to see if, say, an argument to a function call is ever appears outside that function, like does the function put it in a global, or does it return it or something? And if it doesn't escape that function, then the compiler can allocate that thing on the stack. Otherwise, it has to heap allocate it. And of course, if it can't see that function's code, the called function's code, because it's indirect, then it doesn't know, and it has to assume the worst case, so it heap allocates it. Now, it's very hard to predict what the escape analysis will do. It's very clever, gets better all the time. But you can use this -m flag to at least see the decisions it's making. It'll tell you for every variable in your program whether it escapes a particular function or not. And once you've optimized your code, so you've got it down to 3 allocations, you want to lock that in so subtle changes to your code during further development don't mess that up. So you should use testing.allocs_per_run in your tests. It'll tell you how many allocations happen, and you can say this has to be less than or equal to 3. That's a really useful technique for making sure that future work doesn't mess up your performance optimization. So let's look at a few scenarios. We'll start with variadic arguments, those ... arguments. Here's a really simple function that just adds up its variadic argument. And to that function, that variadic argument appears as a slice. So where is that slice allocated? Well, you can see that this argument ends does not escape. It's just used in the function, but it's not put into a global or returned or anything like that. And the compiler can see that too. So when you call sum directly, that slice is put on the stack. There's no heap allocation. But if you call it indirectly through a pointer or an interface, the compiler will put that slice on the heap. So let's get back to the whole business about logger being a concrete type. Here's the whole story. Logger is a concrete type. The log adder method takes a variadic argument, these adders. Okay? So this call is a direct call. So whatever you put there, that turns into a slice, but that slice can be on the stack because log adders is carefully written to not let that thing escape. And that's true even though the first thing that, sorry, I went too far. Yeah, the first thing that log adders does does an indirect call. Handler is an interface, so handler.enables is an indirect call. But that doesn't bother escape analysis because we're not passing that variadic argument to that call. It doesn't affect the analysis of that argument. So if logger were an interface, which a lot of people asked for because it results in a really nice design where anyone can implement anything they want, if logger were an interface, we would be allocating that slice even if the call were disabled, which is bad. And that's why it's a concrete type. Now, that's the start of the logging process, calling log adders. And at the other end, the handler is taking all the stuff you gave it and transforming it into a sequence of bytes for output. So let's talk about how to optimize that. The first code block here is absolutely what you should do almost all the time. Do not go home and say JBA said to do all this other fancy stuff. No. Do this, the first thing, unless you have a performance issue. So what's wrong with this? Not wrong. What's slow with this is that as you continually append to it, you will grow that byte slice. It will have to reallocate to about twice the size. You'll copy everything over. And depending on how many appends you do and how much space you use, you can do that repeatedly. In the second code block, we get that down to one allocation by making a size big enough for our common case. And again, you have to experiment to see what that common case is. But this is actually the number we use in the built-in handlers. One case seems to cover most log lines. And now all these appends will not do any additional allocation. You can get it down to 0 allocations with a sync.pool. A sync.pool is a manual memory management technique. Someone asked yesterday about manual memory management. Go has it. In sync.pool, you can put and get things into this pool. And if you put something and then you get it, you're getting the same one. There's no new allocation that happens. So if you use that, then yes, there's some initial allocation as you build up a pool of things. But in the steady state, everyone's just getting something that someone else put into it, and there's no new allocation. Now we're going to talk about the scenario of passing something, in this case the record, to an interface method. That's an indirect call. So if we used a pointer to a record, that would have to get heap allocated because the compiler couldn't see into the call. And so the escape analysis wouldn't work. It would have to heap allocate the record. And anyway, we want to allow handlers to cause that record to escape. A perfectly good handler takes the record and puts it on a channel for asynchronous processing. So even if the compiler could see into it, there are handlers where the record would escape. So how do we avoid allocating a record? We just copy it. We pass it by value, which means the record can't be too big or we'll spend a lot of time copying. Now inside the record, among other things, there's got to be a slice of adders because users can provide as many attributes as they want in the log call. And if we just use the plain slice, which again is absolutely the right thing to do in almost all cases, just do that. The thing that's crossed out, just do that. But if speed is critical, we can do a little better. We can't use a sync pool for records, though. We decided not to. You can, but it's a bad idea for us. Why? Because users have control of records. Handler writers can get their hands on a record, and we'd have to ask them to free it, or try to free it magically at some point. But either way, they could get themselves in trouble by freeing it twice or holding on to one after they free it. That's a use after free bug. And that's why zero-log was problematic for us. Zero-log, as part of its speed, exposes a pool-allocated value to users. If you use zero log the normal way that you'll see in all the examples, you will never encounter a problem. But if you do something a little out of the ordinary, you can get use after free bugs. And we just didn't want to put that in the standard library. So sync pool is not available to us. So what did we do? We put a little array in the record of size n. And that array holds the first n adders, no allocation. It's just there as part of the record. And then we use a slice if there's more than n. So what is n? If it's too small, we'll allocate on a lot of log calls. And if it's too large, we'll have this large record that has to get copied. Well, we know the answer to this question because we did the research, and it's 5. We know that if n is 5, we're going to capture about 95% of all logging calls. That seems perfectly good. Okay? Last but not least, these adders are just key-value pairs. That's what an adder looks like. It's very simple. The key is a string. But the value is not an empty interface or an any. It's this special type slog.value. And that's the last and maybe the cleverest allocation optimization that we do. So when you construct say a string attribute, the key is just the key, and the value, we call this string value function to turn an ordinary string into a capital V value. So why value? We're going to trade space for allocations. To understand that, you have to understand how things are represented in Go. This is an interface, 2 machine words. The first is a pointer. It's always a pointer. And the second is some type information. This is how strings are represented, also 2 machine words. The first is a pointer to the actual data, the bytes, and the second is the length. When you put them together, like when you assign a string into an any, you get this picture, 2 arrows, 2 allocations. Now, the string allocation is in your program anyway. You have to do that. That doesn't count. But this extra allocation, when you put the string in the any, is what we're going to avoid. Well, let's look inside a value. A value has an any in it, but it also has an extra machine word called num. Values are like, these slog values are like reflect.value. There's a kind, that's a little enum, small integers, that tells you what kind of value is in there. Okay? So now I'll show you how we represent some simple things, and then we'll get to string. So in int64, the number is just the number, cast to a uint64. And we use that whole any field just to hold this small integer. Now, I just got through telling you that everything in an any value in an any is a pointer. So aren't we allocating a pointer to that small integer? No, because in the Go runtime, there's like 1,000 or so, there's an array of the first 1,000 or so integers. And when you construct an any from a small integer, you get a pointer into that array. So yes, it's a pointer, but there's no allocation at runtime. That's a static array built into the runtime. And we do the same thing for floats and a few other types. Nothing here is very interesting. There's a nice function called math float 64 bits that converts our float to a uint64. And we use the kind field, the any field for kind. So now let's look at string. So here's what we do. The length of the string goes into that num field, and the any field holds the string data. Now, there's this function in unsafe called string data that just gives you a pointer to the raw bytes. And it's unsafe because if you play with those bytes, you can get yourself in trouble. But we're not going to play with them. We're just going to store them in this anything, and we're going to use our own internal type just so we know that we actually have this string data in there. So a value, then, is these 2 fields are the any. One is a pointer to the raw bytes, and one is that type. And then we have the length. So we've gotten rid of that extra allocation, because, again, this thing is already part of your program. We've traded one machine word to get rid of that allocation. So when you put a string into a slog value, there's no extra allocation. We also do something clever with time, the time type, in a similar vein. That's all I have for you. I just want to summarize. So the design of slog was informed by almost a decade of prior art about what the Go community developed for structured logging. So we waited a long time, but it was worth it because we got a lot of information about what people really want. Same for performance. You can always make arguments about why something needs to be fast, like, oh, it's in the inner loop. But until you look at what the community actually does, you don't really have a good sense of how fast. So we're able to use that to pick our performance goals. The third point is about designing a backend, like handler. Whenever you have an API where there's a user-facing part and a backend part, make the backend part more complicated to enable optimizations. Because remember, relatively few of your users are going to be writing that backend. Most are just going to use the front-end part. So we made the handler API a little more complicated to enable optimizations. And last but not least, if you avoid allocations, you can often save a lot of time. Thank you very much.